All right, so this video is on section 7.2, the transformations of exponential functions. So to start off, we've got our equation showing a, b, h, and k for a exponential function. So we just want to remember what each part does. So we're looking at a first. So a is our vertical stretch. Vertical stretch by a factor of a. Okay, and then b is the horizontal stretch by a factor 1 over b. So remember that here the factor and b are reciprocals. And then h, again watch the sign with h. H is the horizontal translation. To the right or left. So, and then K is our vertical translation. So up or down. However many units. Okay, so those are the main ideas, and now let's try and put those into practice. But the other thing that I want to point out when we're drawing a sketch of a transformation is our mapping notation. And so remember from our transformations unit that we have the original function and we have a table of values, right, with values for x and y. And then we use our mapping notation to have the points on the transformation. And the rule is that x becomes x over b plus h, and y, a, y plus k. So this is going to be really, really important for what we're going to do next. And you've seen that a lot already. So let's go to it. So in this example, our original function is shown over here. Y equals 0.5 to the power x. And we are going to perform some transformations on it. So over here, a is 3, okay, and h is negative 1. So remember that even though it looks like a plus 1 here, h is actually minus 1. So we're going to first describe these transformations. So a equaling 3 means that there is a vertical stretch by a factor of 3. And h being negative 1 means that there's a horizontal translation one unit left. All right, so now to sketch the graph, what I want to do is come up with some points that are on the original and then see where they end up using mapping notation. So here, my mapping notation is going to be x, y on the original. So if I think of a couple of values on the original, let's do that. I'll do that in blue because the graph of the original is blue. So x and we have y. And the points that I'm going to pick are maybe neg2, 4, and neg1, 2. So over here, neg2, 4, negative 1, and 2. 0, 1, and let's do one more. Let's pick over here at 2, 1/4. our mapping rule, so if I go back up here, our mapping rule is x over b, but b is just 1, plus h, and h was -1, so x minus 1. If we go up, you can see that there was h. And then y is going to become 3y. So that's our mapping rule. So let's apply that to this table of values and see what we get. So this is going to be my transformation. So I'm going to take each of the x values and subtract 1. So -2 minus 1 is -3, -2, -1, and then the last one, 2 minus 1 is 1. And then I'm going to take each of the y values and times them by 3, because that's my mapping rule. So this 4 is going to become 12, 3 times 4, 6, 1 times 3 is 3, and then 3 times a quarter is 3/4. So let's plot those points and then connect them with a smooth curve. So 3 minus 12, -3 rather, 12, oops, is here. Oh, the graph is moved, or those points moved. Let's just get rid of those. I don't know why they moved. There. Oh man, okay. Anyway, we are graphing our transformation. So -3, 12, that's there. And the next point is at -2, 6. That's there. -1, 3. And the last point was 1 3/4. So that's there. Oh, it's weird. That's about there. So now if we connect the, oh man, we connect these, our graph should look something like that. And then we have our transformation. Okay. So next, these questions, maybe if I erase what I wrote there, I'll be able to see what I was asking. There we go. Clean up some space here. The domain and range for our graph. So the domain is that x is an element of the real numbers. And the range, y is greater than 0. Okay. The x and y intercepts. So there are no x-intercepts. And the y-intercept, I can see on my graph the y-intercept is right there. But if I wanted to calculate the y-intercept, what I might do is write out my equation. So it was 3, 1/2 to the power x plus 1. And so the y-intercept all along here, x equals 0, because I'm neither to the right nor to the left. So in my equation, I'm going to replace, I don't know why it's doing it. I'm going to replace x with 0. And then I'm going to calculate what y is. So y is 3 times 1/2 to the power 1, which is simply 3/2, or 1.5. So my y-intercept is at x is 0, y is 3/2. And that was that point right here. Okay, so moving on. Here's another one for you to try. All right, so here, what I would do is first identify A, B, and K. In this one, H is 0. So identify those, describe them, so tell me what effect they have on the graph, and then to sketch the graph, use a mapping rule, use mapping notation. So I'm just going to put down that. So give that a try. So this would be a good point to pause and then try that. Okay, so hopefully you found that A is 4, which means disappear. So in my description, I'm just going to do that up here right up to space. Vertical stretch by a factor of 4. That's A. B is 1/3. So that tells me the horizontal stretch by a factor of 3. Remember that the factor and E are reciprocals. And then K lastly is -5, so that means a vertical translation. And because it's negative, we're going to do 5 units down. 5 units down. So my mapping notation in this case will be that x, y on the original, which is my blue one over here again, I've got the graph for you, becomes becomes x over 1/3, which is actually going to be 3x, comma, a was 4, 4y minus 5. So hopefully that was the mapping rule that you came up with as well. And now what I'm going to do is pick some points on the graph and have those again in my table of values. So x and y. This time I was a little bit lazy and I only picked 3, so -2, 4, 0, 1, and 2, and 1/4. So those are points that are on this original, right? -2, 4, 0, 1, and then down here 2 1/4. So I'm just going to move those 3. I don't have to move a whole bunch. Maybe you pick 4. We should end up with the same graph. So now in my transformation, every value of x I'm going to times by 3. So this should be -6. This remains 0. And this is now +6. And then for y, I have to times the y value by 4 and then subtract 5. So I go 4 times this 4 minus 5. That's 16 minus 5, which is 11. So my first point is at -6, 11. Then I'm going to repeat that with this next value over here of 1. So 4 times 1 minus 5 is -1. And then I'm going to repeat it with the last value, which was 1/4. And if I do that, 4 times 1/4 is 1. Take away 5 is -4. So I'm going to plot these points now that I've got. -6, 11 is there. And then the next point was 0, -1, which is there. And the last one, 6, -4 is way down here. So if I connect those, I end up with this being my transformation. So now let's go look at these other questions about the domain and range and so on. I'm just going to erase this try and erase this to there we go, to have some more space to work here. So just clearing that up, so a bit more space. Okay, so my domain for this is going to be x is an element of real numbers. Oops, I'm sorry, I'm writing the wrong thing. X is an element of real numbers, sorry about that. There we go. X is an element of real numbers. There we go. Alright, and the range, my range is going to be that y is greater than -5. So you can see in the equation, it comes from here, y is greater than -5. The x-intercept, in this case, I'm going to find that using the calculator. And so x-intercept is at negative 0.966. So that was about here, right there. I could do the y-intercept the same way by putting in 0. So what is y when x is 0? 4 times 1/2, 1/3 times 0 minus 5. So y equals 4 times 1/2 to the power 0 minus 5 is going to be 4 times 1. Remember, anything to the power 0 is just 1. So this is really 4 minus 5, which is negative 1. And that's that point right there. We actually found it in our table of values. So 0, negative 1, my y-intercept. There we go. All right, so in the next case, in this problem, and this is taken from your textbook from page 353, and it's about smoke detectors. So this time, it says they contain a small amount of this element here, represented by the symbol AM, and it has a half-life of 432 years. So this is a bit of a throwback to the other section of the chapter where we talked about half-lives. And it contains 200 micrograms, so a very, very small amount. So you want to write an exponential function that corresponds to the graph showing the decay. So you would probably say y equals 200. That's our initial amount, right? That was the amount of micrograms that we have. It is a half-life, so that tells me that the base is going to be 1/2. And time, in this case years, I would say, over the half-life time, which is 432. So there's our equation. Hopefully this looks familiar from the homework from the other day. And now, based on your equation, identify the parameters below. So the base is 1/2. That's this right here, right? And that is because it's a half-life. I can see A, that's right here. That's 200. And that is the starting amount. B, you can see, well, B is really 1 over 432. Oops, that should be a 3. 1 over 432. There we go, that looks better. So there's B. H and K are both 0 in this example. So there we go. We're coming up with an equation that's in this format, right, based on a scenario. And over here we have the graph. Oh, look, and it's in French too. So the quantity, the time in years. There you go. It's kind of hard to read that scale. The numbers start to kind of run together here. But anyway, there's our graph. You can see there's our starting amount, our y-intercept, and so on. Okay. So next, here's another similar one from your textbook that is about a glass of water is warmed to 100 degrees and then left to cool to 20. Every minute, its temperature is recorded in degrees Celsius as a function of time, m in minutes. The data is then graphed, so you have a picture of the graph over here, and the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. So what I'd like you to do is think about how you would write an equation to model this scenario. So this one, we're decreasing at a rate of 25% every 5 minutes. This is our starting temperature. Okay, so think about that one. Okay, so this is a bit of a trickier problem. What I would do if I look down here, the base that I'm going to come up with, so if it's decreasing by 25%, 1 minus 25%, my base is going to be 0.75. So hopefully you saw that, 0.75. Then, what am I after next? Every 5 minutes. So my exponent is going to be n minutes over 5. So the b value is going to be 1/5, right? Because it's decreasing every 5 minutes, decreases every 5 minutes. All right, h in this case is going to be 0. I think I moved something around here. This is down there, my bad. Okay, h is 0. Cool. All right. H is 0, K, if you look at the graph, you can see there's K, it's at 20. And this one, the reason why it's so tricky is because we don't really know what A is. So we're going to have to calculate A in this case. So this one, this is a bit of a trickier problem to get the correct model. So I would say y equals A times 0.75 m over 5 plus 20. And now I'm going to pick a point to determine the value of A. And the point that I'm going to pick is probably this one here. That's sort of an easy one to use. So 0, so 100 equals A 0.75 to the 0 over 5 plus 20. So there, I've got a bit more space now. So 100 equals A times 0.75 to the power 0 plus 20. I might sort of start by subtracting this 20 from each side and get 80 equals A. This 0.75 to the power 0 is just 1. Oh, there we have it. There is our A value. A turns out to be 80. Okay, and now we have all of the components to be able to write the equation. So I would say y equals 80. My base is 0.75 to the power m over 5 plus 20.